So for the second problem in tutorial 2, problem 2b.1, different choice of coordinates for the following film problem. So rederive the velocity profile and the average profile in section 2.2 of this textbook, or example 1, the flow of a falling film in your week 3 slides by replacing x with a coordinate x bar measured away from the wall. Okay, take note of this. That is, x bar equals to 0 is the wall surface, and x bar equals to delta is the liquid gas interface. Show that the velocity distribution is then given by this equation, and then use this to get the average velocity. Show how one can get equation 2b 1.1 from equation 2.218 in the week 3 slides by making a change of variables. So let's look at the profile of a falling film problem. So this is your wall, and as the question state, coordinate x is measured away from the wall, whereby x bar equals to 0 is the wall surface. Okay, so this is your wall and your wall surface here. So that means x bar is equal to 0 over here, and x bar delta equals to delta is the liquid gas interface. So this is your liquid, this is your wall. So this is your liquid and this is your gas. So the liquid gas interface means this line. Okay, for example, so this is x equals to delta, and whereas over here this is x bar equals to 0. Alright, so because we have a falling film, okay, a liquid, therefore there are two profiles. One is the shear stress profile, tau, and the velocity profile. So the stress profile will look like this, whereas at the wall surface you will have the largest stress, the tau will be the largest, whereas at the gas liquid interface it will be the smallest. That means it is 0. So you look at the point here. Okay. However, for the velocity profile, it will be faster on the liquid gas interface, but at the wall, okay, at the wall surface, it will be near 0. Okay, so this is a vertical downward. So the beta is the angle between the vertical wall to the falling film angle. Okay, so how to approach this question? So we know that, okay, sorry. We know that the tau x bar z over the x equals to rho g cos beta. Okay, so we will integrate this equation. Therefore, tau xz equals to, d tau xz equals to rho g cos beta to dx. Integrate this problem, we shall get tau xz equals to rho g cos beta multiplied by x bar plus c1. Okay, in this case we know that at x equals to delta, which is this line, tau is equals to 0. Okay, so this is your boundary condition. At x equals to 0, sorry, at x equals to delta, tau z equals to 0. Okay, so we substitute the boundary condition into the problem here. Oops, where's my mouse? We get 0 equals to rho g cos beta. Substitute this with delta plus C1. Therefore, C1 is equal to negative rho g cos beta times delta. So we now have C1, therefore we can substitute C1 back into the original equation here. Okay, so therefore tau xz is equals to rho g cos beta multiplied by x bar minus rho g cos beta times delta. Okay, we then can rearrange this equation into a simpler form, which is rho g cos beta multiplied by x bar minus delta. Okay, then we take delta out into the equation, which gives us rho g delta cos beta. So this one has to be divided by delta minus 1. Okay, we can again rearrange the equation so that okay, so that negative rho g delta cos beta equals to 1 minus x bar over delta. Okay, then over here we have the Newton's law of viscosity given as such. Now dvx over dz should equals to 0, right? Because there is no velocity in the x direction. There is no velocity in the x direction. So your flow in the z direction, therefore you have Vz. However, your flow does not flow in the x direction, it is not flowing up. Okay, so Vx is equal to 0. Therefore, that means that this this component here should equal to 0. That leaves us with negative mu multiplied by dv dv okay, sorry, dvz over dx bar. Okay, so we substitute this into this following equation. Therefore, that gives us with negative mu dvz over dx bar equals to negative rho g delta cos beta multiplied by 1 minus x bar over delta. Okay, so we move the equation, rearrange the equation so that we get dou vz equals to rho g delta cos beta over mu multiplied by 1 this. Okay, then we will have to integrate this equation. Okay, so integrating this gives us vz equals to rho, oh crap, okay, let's write this one down again. So rearrange gives dvz equals to oh no. Okay, please wait for a while. Equals to rho g delta cos beta divide by mu, okay, minus x bar divided by delta, okay, and dx. Okay, rearrange this equation. Therefore, integrating this gives us vz equals to rho g delta cos, integrate it against x bar, gives us this x bar equals to, sorry, minus x bar square over 2 delta plus C2, okay? Don't forget to add your constant at the end after your integration. Okay, now, in order to find the C2, we need to identify the boundary condition. So remember that our velocity profile looks like this. Okay, where this is x bar equals to 0, this is x bar equals to delta. Therefore, at x bar equals to 0, your velocity should be 0. That is your boundary condition. At x bar equals to 0, your vz equals to 0. Substitute these two in, so get 0 over here, rho g delta cos beta divided by mu, and this should be 0 minus 0 squared over 2 delta plus C2. Therefore, your C2 equals to 0. Okay, so meaning to say this equation, okay, C2 equals to 0 is substituted back into this equation, we will get Vz equals to rho g delta cos beta over mu multiplied by x bar minus, we can fraction this out, and x bar square over, delta. Okay, so we can take out the delta, and that means that Vz equals to rho g delta, okay, take note of this, square, because in the equation it wants us to find the equation. So in the equation given that we should prove has square, so we take out the delta, cos beta divided by mu. So this guy here has to be divided by delta. Am I correct? Okay. Minus 1 over 2. And this one should be x bar over delta square. Okay, because over here we have to divide by delta again because we take delta out here. Okay, and this will be your final solution.